Alright, here's a quick look at another IB high-level problem involving integration by parts and volumes of revolution. This one is a little bit easier to evaluate than the other one in terms of determining what the shaded regions are, because our parameters are x equals 1 and x equals e and y equals 0, which is the x-axis. So we're basically just going under the curve with these boundaries. A little bit easier, again, to find our bounds here. The first case, I evaluate the natural log of 1 over 1. The natural log of 1 we should know now is 0. So that's the first point, 1, 0, x-intercept. And the second point is the natural log of e over e. The natural log of e is 1, so we have 1 divided by e. We have to figure that this is going to look like a logarithmic function in spite of the dividing by x. So this is going to have that concave down, increasing at a decreasing rate, and we can kind of estimate the area here, but it doesn't matter because we got to revolve that thing. So this is the integral then that we're trying to find. And squaring both natural log of x and x squared makes it a little tougher to see the integration by parts algorithm. It's easier to break it up into a product. So we have 1 over x squared as one function and the natural log of x squared as another. Also be careful how you write natural log of x squared. We have to make sure that it's the natural logarithm that's being squared and not just the argument of the natural log. So we choose our u's and our v prime in the best way we know how. And I can see right here that integrating the natural log of x squared, finding its antiderivative, is going to be a challenge, whereas anti-differentiating 1 over x squared should be easy. So that makes a really clear choice for me as to what to choose for u and v prime. Differentiating the natural log of x squared, remember the chain rule, we basically drop down the 2, bring the power down to 1, and then take the derivative of the inside, which is 1 over x, and that's where this comes from. And then in exponential form, x, or power form, x to the negative 2, we just raise the power by 1 and divide by the new exponent. That's how we get negative 1 over x, and we can check that back by differentiation. And the algorithm for integration by parts is the same as it ever was. And so once again, it is a definite integral, and we can actually recognize that the u times v was already integrated, and therefore it has its boundaries in place for evaluation by the fundamental theorem of calculus. Here, the u, v prime have to be multiplied together in a way that makes it, again, easy to integrate if we can. The problem here is I recognize once again that we're going to have another product. In other words, I'm going to have to use integration by parts one more time. This time, however, the 2 natural log of x is actually very easy to anti-differentiate, and so I'm going to switch around my u's and v primes here based on the new information that's given. Before I do that, I'm going to evaluate this integral right here so we can get that knocked out. And so the whole mess in here simplifies down to the opposite of 1 divided by e. And then we're going to add, notice that, by the way, I forgot to mention, we have the negative 1 over x. I brought the negative out, and that's why I'm adding the integral, not subtracting, so that shows up down here. But here, we're integrating from 1 to e, 2 times the natural log of x, x to the negative 2. As I said, the best choice here now is to make the natural log your u and make x to the negative 2 the v prime. And as you can see, it actually does make some really nice numbers, so that when evaluated now a second time into integration by parts, we get our u times v and our u prime v, and that's just a power function, very easy to integrate. And it makes a nice integral, easy to evaluate, and we end up with 2 pi minus 5 pi over e. Just to check to see with the technology, we can see that they have 2 minus 5 over e times pi. We distribute the pi. We end up with the same result that we had. So, feeling good about that. As you can see, the volume is only around a cubic unit, so there's not very much stuff being rotated around here. But anyway, thanks for watching.